Welcome to those of you online and everybody here in the room. This is the finalists for the openBIM Awards 2025. And first today we are going to hear from 3 projects in the category of construction for buildings. Without further ado, let's get started, and I would like to invite to the stage Guangdong Airport Authority.
Ladies and gentlemen, good morning. I'm Manlei from GA. Here are my team members, Colonel, Yuchuang, and Weixin. It is a great honor to participate in this competition. Now, we would like to share our achievement in intelligent construction and openBIM practice. Now, I turn over to Colonel.
Good morning, I'm Colonel. Let me start by giving you a brief background to the project. Guangzhou Baiyun International Airport, one of China's 3 major international aviation hubs, ranked as the 10th busiest airport in the world last year. Now, the Phase 3 expansion is a truly ambitious undertaking. It represents an investment of about 7 billion euros. It includes 2 E-class runways and the world's largest single terminal building. Altogether, it makes the list the biggest airport project currently under construction in China. GAA is leading the project. It brings together 12 specialist disciplines and involves more than 145 contracting entities. So, faced with such a vast and complex, challenging, tight schedules, demanding operational needs, we turned to tailored openBIM solution. We applied IFC for data exchange, BSED for terminology standardization, IDS to ensure information consistency, BCA in smart operations. Based on that, we defined exactly what was needed for the OIR, PIR, AIR, and EIR. And with that, I'll now hand over to Yuchuang.
Thank you. And ladies and gentlemen, hello. Next, I will introduce our openBIM practice to you. And before the implementations, we have some preparations which includes the software environment, process, standards, responsibility matrix, and BSDD. And I will show you that. I will show you individually. And the first one is this software ecosystem maps. And this map shows all software we use in this project. And besides, we also created some useful tools by ourselves to help, which includes the IDS toolkit, the IFC database, and the CDE platform. And I will discuss later. And IFC and BSDD plays a very important role in data exchange missions. And the next is about our process map. And this map shows the information delivery process. By using IDS and BSDD, doable digital requirements are prepared, and each discipline can generate standard IFC models. And after reviewed, those IFC models will be gathered together in the CDE to continue. And the next is our implement standards. Our implement standards mainly includes the ISO standards, buildingSMART openBIM standards, GB national standards, and MH aviation standards. And the next is the responsibility matrix. The responsibility matrix for this project is shown on this screen, and to ensure all the parties have well-defined responsibilities. And the next is our BSDD. We reviewed the component categories defined by the CAA of China and compared them with the IFC standards. And we find that some of the components are not covered by the IFC. So we created and uploaded 71 civil aviation classes and then related 195 properties to the BSDD, as you can see on this screen, to enhance the information expression abilities of civil aviation. And that's all about our preparation part. And next, we will go into the implementation part. And to summarize, the implementation part is all about the EIR to AES, and then to the IFC, and use BCF for review. And after review, those useful information will be gathered in the CDE platform to continue. And the EIR of this project is based on the project standard system. IDS fields are created by BSDB, thus to enabling IFC-based data to exchange. And we develop an IDS toolkit for converting EIR into IDS in a more efficient way. The generation of IDS is driven by classification codes in the aviation area to determine the applicabilities of entities. And moreover, it is connected to the BSDB, which provides a standardized semantic foundation for IDS creation, thereby enabling the consistent selection of object classes and attributes. We created over 5,000 IDS templates to cover all EIRs, and all these IDS templates have passed the verification of the IDS audit tool. And for IDS checking, IFCDB can significantly improve efficiency. For instance, in the case of over 100 IFC models, traditional way of IDS check by opening each model one by one would take about 4 hours. And however, using our way, it takes 5 minutes, saving more than 98% of the time. And we follow the process of the openCDE BCF for BIM collaboration management. For instance, when functional requirements change, it can lead to modification. Because all the IFC models have been published to the CDE, it allows project stakeholders to immediately start the model review process. And in CDE, engineers from different disciplines can discuss and create question lists with BCF at the same time. And after that, BCF issues will be generated, including details such as the BCF title, description, and with the help of openCDE BCF API, we can mark these issues and export them to BCF file, and team members will be notified through email. And after they get those emails, the responsible parties will resolve their issues, and the BCF file can be read in their individual software, like Autodesk software, and the BIM engineer can easily find where the problems are and correct them. And after that, a new version of IFC model will be delivered to the CDE. And after the final review and approval, the latest version of the model becomes available to all users. And our CDE mainly includes 3 components: BIM4, IFCDB, and CMP. Additionally, large AI model also help us to understand metadata. And the first is the BIM4. BIM4 really focuses on model file management, version control, and BIM collaboration format. Based on our HLOD high efficient indexing, it can handle massive model integration works. It also helps model review and class detection. And additionally, it supports the management of IDS documents and other related information requirement files. And the second is IFCDB. It's a specialized database, and it can decode IFC files into individual IFC entities, including their attributes, geometries, relations, and IFC data search and extraction can be performed directly using SQL or even natural language like English. And during the IDS inspection phase, checks on all models can be conducted with only 1 click. And the CMP is used for project management, task assignment, real-time communication, and use case management. And that's all of my part. Next, I will hand over to Ms. Wei to continue.
I'm Wei Xing. Use cases. Based on our BEP, BIM use cases have been carried out across all project phases. These applications are crucial to achieving project objectives and boosting efficiency. Next, we will highlight key cases. First, process management. Our IFCDB and the CMP platform link resources to digital plans, enabling real-time tracking and rapid adjustments. This ensures 100% major milestones, 90% secondary completion, and shorten the project by 99 days. Second, quality management. We use AR and 3D laser scanning to compare point cloud data with IFC models. Automatically generation deviation reports. This links digital design with physical construction, improving precision both on-site and in design. As a result, we boosted quality inspection efficiency by 80%, saving 30 days on measurement. A great example is our automated plastering robot using IFC data for automatic navigation and planning. It performs high-precision plastering with minimal human intervention. It achieves a 3 mm precision tolerance, works 8 times faster than human, and reduces coloring rates by 30 times. In this project, we adopt the openBIM workflow and use cases such as procurement design and construction, supply information management, and digital fabrication. These application scenarios provide clear goals and implementation paths for the smooth progress of our project, ensuring that work can be carried out efficiently around the whole task. Now, I will hand it over to Ma Lei.
Thank you. Next, I will introduce our own feedback to you. We have completed over 5,000 ideas instruction and marked more than 3,000 BIM issues by BCF. Currently, 45 types of software have been connected for collaborations, and about 2,000 apps models have been exchanged, and more than 10 types of intelligence devices has been used on site. So, what has this data-driven approach actually achieved? Let me share some key results. The total cost saved is about 18.3 million euros. The space requirement of MEP equipment has been reduced by more than 2,200 square meters. Intelligence robots have increased the construction efficiency and the processes of the key processes by 8 times. Our goal is to build a truly data-driven project and based on openBIM and ISO standards. Right now, GAA is using BIM models to build a digital twin platform for Guangzhou Baiyun International Airport, which will be used for the airport daily operation. Together, we are not just building an airport, we are defining what a smart airport can be. Thank you.
Okay, next up, I'd like to invite Hing Engineering for their presentation. Thank you.
Good morning, everyone. I'm Eric from Hong Kong, representing the Hong Kong Private Sports Park. Hong Kong Private Sports Park is a 28-acre sports complex consisting of 3 major sports facilities: a 50,000-seat stadium with a trackable roof, a 5,000-seat sports ground, and a campground of 10,000-seat indoor stadium, and 3 more. It is a design, build, operate, transfer project. Contract sum is $3.85 billion. We won the contract in 2018 and started the construction in 2019. But unfortunately, soon after we started the foundation construction, COVID-19 started, and then the global lockdown. And no matter how, we have to complete it before the end of 2024 for the coming National Games of China. We needed to find a way to push our project forward under a circumstance that we were unable to have face-to-face contact with self-design and hundreds of factories around the world. Over 70 design offices with more than 500 engineers scattered around the world work for our project at that time. Previously pioneered in the depth of being used, to make sure that all BIM engineers are familiar with and work smoothly on the open platform. We send 40 BIM engineers to learn how to use it. As you can see on the slide, we were dealing with the sophisticated building element with complex profiles such as retractable roof, a curved external wall cladding, hydraulic stage pocket, telescopic seating with both seating system underneath. We had to modularize our construction as much as possible. To do so, we needed an open platform to communicate with our designers, eventually with our factory. Not only the crews in the factory, but also the machines. Our teammates work thousands of miles away apart and at different time zones. Moreover, similar to human language, they work with different softwares that fit their own purpose. To communicate freely, we needed a converter to convert information from different software into a universal form, such as I see in the slide, that enable us to exchange the data through the fabrication construction collaboration. COVID-19 lasted for 2 years. I was not a big fan of BIM at first, but I was definitely pissed at that time. And the open BIM came to my rescue. It allows us to exchange data without seeing each other. It enabled me to whatever I wanted to change my house during the lockdown. I was so amazed that when I knew that I could use the technical model to design all the steelworks through the massive steel roof to a tiny little bit of handrail and send the model to the factory for fabrication. No more lengthy conversion from shop drawings to fabricating drawings. Faster production with almost zero problem. And my colleague wrote as well.
Thank you. Thank you, Eric. Okay. In terms of the open BIM utilization, we selected the statistics highlight on one of many use cases to share more detail regarding the implementation, workflows, challenges, and solutions, which cover the entire construction from early stage to final stage. And AI enabling for planning sequencing and more feature coordination. The main challenge is very short time frame for the enormous workload. Regarding the software assistant to meet all the requirements. Automated statutory compliance checking and TFMA facade system monitoring rely on real-time synchronization, enabling agile data conversion. Implementing a fundamental digital twin is a big challenge, as shifting people mindset remained one of the toughest obstacles. I will go one by one for all the use case. In first use case, AI-enabled planning sequences, we create an initial schedule, but anticipate delay due to the raw cat validation. To mitigate this, we directly import IC property values to leverage an accurate cat profile using completed all-power data. The second use case focuses on steel structure development. From fabrication to installation, use BCF to identify design risks early, while subcontractor create fabrication model alongside design. This model optimizes construction sequencing, material lasting, logistics, and quality assurance. The third use case highlights automated compliance checking with solid BIM. As design evolves, BIM updates are essential, but manual checks are too slow. Models are converted to open IFC format for compatibility, enabling effective cross-platform analysis and compliance. Use case 4 tackle managing over 5,000 units room in this project, each with specific needs for security, classification, functionality, and controls. All switch and socket follow strict location and pattern rules. We did an estimation that even with 100 team members working together, only 10 rooms could be coordinated daily, requiring over 1.5 years to finish manually, causing delays until our digital solution was introduced. Use case 5. Show how we bring technology to the frontline operation. This highlights the need for digital transformation, requiring integrated software and systems. This is the last use case, use case 6. Focus on integrating BIM with the logistics system. Most of the project managers often struggle to manage and oversee issues beyond their direct responsibility. To address this, a digital monitoring system was implemented using open format standard for seamless information exchange. After that, I also share something about the benefit using openBIM for the integrated solution. As highlighted earlier, construction site generated dynamic data every second to support agile decision making for the project management team. Hing developed its own system to collect relevant data for various sources, including the sensor, system, and reports. Given the multiple data sources across different platforms and software, a unified format is essential to enable seamless data conversion, meeting safety, environmental, and progress monitoring needs. The next one is structure about the organization of this central management platform. The central management platform integrated relevant software and workflows. Some data is sourced through Amazon Web Service and processed using Python. The structure in our database. You can see the top. Power BI is used to transform this data into clear and actionable track for reporting. In this project, we also use the BIM cave. The BIM cave is often seen as useful only for in the design phase for improving the design. However, it also helps inline team plan space and equipment logistics in an immersive way. Additionally, it leaves a lasting impact on training when used for safety training, ensuring deep and sustainable learning. Please take a look about the outcome as a chart. The full chart highlights the gap in compatible authorizing software, which we solved by using the openBIM format. In the middle here, you can see they cannot interoperate for each other. Besides that, we also have some innovative approach with the openBIM utilization. For innovative openBIM application, we would like to share two cases. The first involved utilization information delivery specification, IDS, and model view definition, MVD, to meet security information requirements. In the Haahtela Sport Park project, some areas are covered at high security level containing confidential BIM data. To facilitate progress, coordination and information exchange are unavoidable. We rely on MVD to isolate sensitive data during release. Once completed, sensitive data can be safely distributed to specific authorized groups. The second case is about location, because it is located in the city center with many nearby stakeholders. For actively plan its construction site management to minimize impact on group with special needs. Using the government common spatial data infrastructure and OpenGIS platform, which provide key data like demographic, land use, traffic, and tidal information. We ensure informed decision. For instance, when delivery is still stressed by sea, on the ocean, we use tidal and seabed depth data to ensure safe departure. This is a lesson learned. There are the lessons learned regarding contractor method. We aim to encourage the adoption of openBIM by including its application in contract flows. Rather than specifying particular software, we also emphasize clear use case management with the prioritization outlined in the BIM executive plan to ensure all project stakeholders understand and adopt openBIM as early as possible. Moreover, we have two recommendations for improving openBIM. The first issue was IFC fabrication misalignment due to native software setup. To address this, the information delivery specification IDS should be integrated in the exchange information requirement, included in the BEP and protocols, and supported by robust model exchange tracking mechanism. At the bottom second encounter, the growing demand for AI to address real-world problems highlight the importance of openBIM as the ideal solution. Open data accelerate AI learning and develop by removing barriers to data access and extraction and enable AI to resolve problems effectively. This is some picture for the project. Just the last one. Last but not least, the key openBIM metrics and come out. Over 10,000 tons of the fuel were used, equivalent to the rate of 3 Apple hours, and 55,000 meters square of facade was constructed. Productivity increased 20 times, and report handling time was reduced by 90%. I also have some data as mentioned about this. We are not the huge number, but actually we focus on very useful issue for each PCF. So around 100. So here is our team representative, and we are end of the panel here. Thank you.
Thank you very much. Now I'd like to invite our final presenter in this category. It's Haahtela from Finland.
Good morning, everyone. You. So hello, my name is Axel Lindberg. It's a pleasure and an honor to be here today. I'm representing Haahtela, a Finnish construction company, and I'm going to tell you about one of our more unique projects today called Katajanokka Pier, and especially emphasize the openBIM use during the delivery of this unique project. But before we jump in, some key facts regarding this project. Mixed-use development. We built an office and a hotel under the same roof. Approximately 20,000 square meters. So compared to our previous presentations, quite a lot smaller, but nevertheless, main structural material cross-laminated timber, and this is perhaps what made one of the key things that made this project especially unique was the use of timber as the main structural material, which we can see here in the picture on the left side. The wooden surfaces there are cross-laminated timber. And as previously mentioned, project delivery by Haahtela, us and our client here was Varma Mutual Pension Company. But yeah, openBIM throughout the project. This slide kind of works like a table of contents for this presentation. We'll shortly assess the design phase highlights, including BIM-based collaboration across the disciplines, communications managed via VCF workflows, and so on. The main emphasis of this presentation will be on production planning and openBIM-enabled production, including 4D scheduling and sequencing, and tag production, and how we implemented openBIM solutions in tag production. We'll also shortly assess the use of openBIM on site, some key discoveries we made regarding the use of openBIM models on site and enablers. But yeah, design phase highlights. This process is probably quite familiar to most of you. We have the native design environments, architectural, structural. We had some specialized niches, parking robots, so on. They produce their IFC models. We aggregate them together, and then we perform the quality control. We check for hard and soft clashes, but we also do data validation. This report is then relayed back to the native design environments through the BCF standard. This is a continuous iterative loop, of course, in which we just improve the design slowly but steadily. And the goal here is to have a fully coordinated design, but also valid designs. Because valid designs in turn enable the next part. Extensive use of openBIM for detailed production planning. This is perhaps the highlight of this presentation. Of course, I'm a bit biased since this was my job, but superstructure, yeah. We did the superstructural works through a 4D schedule that was very precise. It was on element level and by the hour schedule. So really accurate schedule. The interior works were executed using tact production. Tact production in itself is a topic I could discuss for quite some time, but time is of the essence here, so we'll leave it that it's just location-based planning on steroids. openBIM, and this is actually a statement, that the last thing, that openBIM provided the foundation for each of these processes. But a few words regarding the unique timber structure in this project. We had about 2,500 unique CLT elements delivered to site and installed. And the scheduling was down to the hourly level and on element precision. It was deemed necessary to also model the support struts, which can be seen here, just to ensure that we didn't have any soft clashes and ensure the installation sequence. Element installations was conducted during an 8-month period, and we were able to deliver this unique structure on time. And here we have a process chart describing how the data flow from design to element installation actually looked. And as you can see, IFC is present in this process chart. Of course, everything starts with the element, structural design, element design, and then we get down to element assembly codes. So we get unique codes for each element, which in turn is embedded into the IFC model. Then we drive the IFC model into Synchro 4D Pro, and then we sit down with the structural engineer. Here the strut model came into place. So we just virtually built the building itself. And when we had a sequence that was safe to do, then we connected our element assembly codes to the timeline. And voila, suddenly we had each element connected to a time, hourly based, which in turn provided us with, yeah, sure, we had a sequence, we knew the factory could produce the elements in the correct order and so on. We could apply the just-in-time principle. We only got to decide what we needed and so on. But also this, we had superb situational awareness, since we knew on an element level and hourly level, are we in schedule or not? And of course, we had deviations. This is construction, and we reacted to those. But we had the situational awareness. We knew if we were late or not. And here is a short rendering of how the structure rose. In the left corner, we can see the date. So this is quite quickly rendered. And yeah, we also modeled the weather protection tents and how they would travel was of tracks, so to speak. Here we can see they move forward like that. And this was an 8-month period, but every element had a certain time, a certain hour of installation. Then we have the tech production, which in turn enabled us to do the interior completion within 1 year. We built 154 hotel rooms between October of 23 and May of 24. And this was thanks to tech production. On the right side, you can see the tech schedule and a screenshot from the model. And here we can see these are like the locations, and then we have the timeline here. So we have just smaller areas, smaller work packages, and we apply like the assembly line on the construction site. But this in turn requires us to know where we have work and how much work we have. And here we use openBIM like this. The key was to identify the location of workload, but also the quantity of workload. And we did this through quite simply defining preliminary tagged areas, do location-based classifications of the IFC models. For example, there we have a mechanical model, I believe. And then we did location-based quantity takeoffs, which in turn gave us location-based bill of quantities, which in turn could be translated into workload or presence of workload. And then suddenly we could iterate the production areas and make this schedule actually doable. But this was what was a key, how we used openBIM in the interior works as well. Of course, that is quite difficult. You have different kinds of workloads depending on the discipline and so on. But I would say we managed. Then openBIM enabling on site. We have these wonderful models. We have lots of data, but we also have lots of people who are completely ignorant of this fact because they just don't know how to use them. And we apply the philosophy that everyone has access to the model, regardless of what you do. We had Solibri model available for all, and we used the Dalux mobile viewer. And of course, it's one thing to have them there, but we also provided coaching. If you're interested in using the models, visualize this on your phone where you're doing installations and so on. We made it possible. We helped and coached. We also did some coaching on quantity takeoffs for contractors. How can you get the most value on this model? Because we put a lot of effort into the modeling of the detailed designs. So I would say it's a key thing that we get the most of value out of them as well. Main achievements in this project. Successful collaboration through openBIM standards. I would say we did that. Unique timber structure schedule met with minimal deviation, while tag production enabled full interior completion within 1 year. It was quite the achievement that also. It was really a unique structure. openBIM successfully adopted from project start to handover. Reduced risk and enabled decision making. Perhaps this couldn't be highlighted enough. It's one thing to have the model, but actually use them for decision making, for steering of production and so on, is something completely else. And then one good thing, Katajanokka Pier, with its wooden structure, is actually a carbon sink. Next slide, we have our main partners in this project. This, of course, wouldn't have been possible without them. And I would say that was it. Thank you very much for your attention. I hope you enjoyed this presentation.
Thank you very much to our first three finalists. I'd now like to open up the floor to any questions to these first three presentations before we continue with the next category. Any questions from anybody?
I had a question about
someone raising their hand at the back, but just keep it to the.
Please stand by. It's a very impressive product and you like all the material. But how would you work with installations in this actual
You just through it, just a second, just get back into the
track?
And then if you hide it, yeah.
Thank you. Very good question. So the deviations were mainly the deviations, as in this presentation, were mainly schedule deviations. They're not like geometrical deviations in the material. But the schedule deviations, of course, were delays and so on, which hindered production, which in turn were related to deliveries and so on, that we didn't want elements the following day if we didn't install anything. So that was the main thing with deviation. The timber elements in themselves were made with quite, I would say, truly high tolerance. And actually, the structure there were any paper element drawings used. They were from the model machine made in factory according to the element designs in the IFC model.
Yeah. But we can start
Yeah, exactly. So I was wondering, was the geometrical deviations that occur due to natural elements like weather, etc. So after glazing, you get wood works, and how do you implement changes to the wood back into the model and into the product? I could say that the sound of chainsaw was quite present, quite a lot. Yeah, of course. The wood is a natural material. I'm not personally an expert, but of course it swells with humidity. We built it during the summer, and of course, for the beginning of summer we have dry air, and end of summer we have really moist air, and it swells and lives and so on. Of course, it wasn't a big issue with the facade element installation with the structure. Quite a lot of chainsawing was made due to these natural fluctuations.
So, great presentation. I have. That's why we decided to simply ask questions in a row so that we will change directly.
It might be good if you just help to pass the microphone between them because we've only got one.
Regarding IFC part, of course. Have you had difficulties mapping all objects in that case, or finding proper identities and types, plus properties that you will definitely need? And in the presentation, I haven't seen any BSDB idea or using anything in that area. How you solve the property area and details. There's a connection like mechanical fastening, and there are, in some cases you can use steel, but in most of the cases you can solve that directly with timber. How you do that? But all these questions you can answer that.
Very good question. The property and management of data properties and so on, standardization. We have our own company standard which we follow in this project, and what data should be where, and property-wise, what was required from the designs and so on. So we went on a company level in this project, not using international.
We can say way. Tensile structure that you have shown as a temporal protection, or how you solve that with IFC. That's because it's pretty hard.
To be quite honest, it wasn't the most successful, the weather protection that we had to modify quite a bit. But it was a nice thought at least. You are considering like the data information, or is it, yeah. It was mostly the weather protection tent that you saw in the rendering was mostly geometry, only to visualize which areas were protected at certain times. So it was not perhaps, of course, it was made by the contractor who actually built the scaffolding and the tents themselves, but it was mainly geometry was the main value gotten out from it, not the data itself.
More questions?
Yes. So this example was a good example use case for logistical planning and site planning and logistics. Why did you choose for only one use case? Is there did you also consider to use the data for other use cases, for instance, for sustainability policies or things like that? Or are you going to plan that later, or SEA?
So, well, the reason for that is quite simple, because that's my job. I do schedules and production planning, and I really focus only on that aspect. Yeah, a bit of a boring answer, but yeah. But of course, yeah, the possibilities are limitless. Then what else it can be used for? But one of our first projects where we did this super accurate scheduling on this level, and kind of a test bed for future projects, how this could be implemented and based on practices, lessons learned, and so on.
So, next question to
We've probably got 2 more minutes for questions, all right?
Yeah, okay. So, next question to airport project, very impressive presentation. You have mentioned BSDD. Have you had difficulties as well on BSDD implementation, and what most interesting challenges you were facing with BSDD, and have you had a contact with airport domain? You know, design the airport domain. Are you involved in the airport domain? And airport domain has developed the BSDD dictionary for baggage handling. So maybe you have checked that dictionary, and that was helpful for you as well. That's my complex question, but we can try.
Question, and we do have a lot of challenges by using this BSDD. The most challenge for us, I think, is the Chinese word. I don't know whether you guys know how to write Chinese, because our Chinese have a lot of, maybe for one meaning we have a lot of different explanations, so that we have to unify it, because when maybe some client or maybe the owners said in one sentence, maybe others said in another sentence. It seems different a bit, but for us is the same order. So we have to create our own BSDD to unify all those sentences together. And then, as we mentioned in this PPT, we compare our aviation words to the national standards, and we unify them and enhance the BSDD to have a lot of words to put in the BSDD to make these things become real. And that, I think that's our biggest challenge, and we do have do a lot of work on that. Thank you.
And the question about the airport
We do participate in the airport teams as a member, and to use our BSDD dictionary to our real project, and just to make the BSDD from the standards to become real. Thank you.
We have time for just one more question.
Thank you very much for your presentation and also the use cases you showed. I've got a question about the lessons learned. So if you would do another airport, what would you do improvements you would consider for the next one?
And we'd like to know with the license, whether we want to make another airport and.
Yeah, if you do it again for the next airport, with the lessons learned, what we should improve, two things would improve, which you do differently than you did now.
Okay. So thank you for your question. And I think we do have some details to improve. First, we will continue to enhance our BSD dictionary, and then we will do some works to make our CD platform more powerful, because during our process, some of the users that is very difficult to understand and to use. And the next step, we will simplify the interface and let them to use it more easily. And the next, maybe we will do some lectures and do some presentations like that to make our employees much more to know the all open standards more and to participate in this open environment and bring more people to this environment to make our work more easy and efficient. And we also use AI, the large language models, to help us by our coworker. Thank you for your question.
Okay, thank you.
Yeah, very last one.
Yeah. Also great presentation we integrated, especially the steel part. And regarding steel fabrication, what was the most big three challenges you were facing it? And what issues you were facing with that part? Of course, we have steel construction fabrication project.
For the steel is very special for this, especially for this project, because this project is not only consider the normal steel for the detailed collection only. We also have to consider this is one of the structural calculation of the chamber. That's why we have to generate one more model, which is place model and P-camber model. You can understand for that kind of coordination. Our before the designer will build something which is place with the calculation, but for our construction fabrication, we must build the fabrication model with the P-camber.
Maybe 5
so
and 6
we have
you
to
can
generate
download at
another
lunch.
with the
7 and
data,
8.
generate that model with using the IFT, convert that kind of data for the consultant or endorsement. This is also a lot of process. And
I would like to supplement a little bit. I think the most important thing at first is to kickstart the fabrication, and then we will have different models. Our structural engineers will design not only the permanent final settlement, but also the displacement during the process. So we have a 3D scanning set up in the field, and then just monitor the entire steel roof structure. So to make sure that the displacement in the post is in line with our prediction.
To supplement more information, so it's a long span structure. It's more than 100 meters span. 180 span. Just for your information, before and after we fully loaded this steel structure, it dropped down by 500 mil, half meter. So we have to control the tolerance very carefully. So we have 3 steps for QA/QC. First step in the factory, we do the laser scanning to make sure this is under our estimation for the P-camber structure. And go to the site. Before we pre-lifting, we do one more scan. And we have to finish in 2 hours because all the machine is ready. So we make sure we jack this up within 24 hours and do the welding process. And this part, we also spend 2 hours to make sure when it dropped down, it's under our estimation. Before, at that moment, it's just half loaded. We need to estimate it correct or not. And finally, when we go up to the top level, to the roof level, We also do to make sure each step is under our expectation. Make sure the camera is dropped out exactly what we want. And why we do this? Because this is a retractable. If it closed, if it not exactly match with our estimation tolerance, it will stop. It will get stuck. So this is a very high precision project. Yeah, everyone will enjoy this. Thank you.
Okay, thank you for all the questions. We are already 10 minutes over, so in order to finish nearly on time, I think we need to wrap up there. So thank you to all of the presenters. If you could please take your seats, and we will start with the next category, which is construction for infrastructure. Thank you. Yep. So first up, I would like to invite Nathan from Holland Group.
Okay, thanks everyone. My name is Nathan B-Plate. I'm a senior digital engineering manager at Holland Group in Australia. Holland Group projects primarily in Australia and New Zealand. Tier 1 contractor, I'll try and go back for work at hand. About 6,000 direct employees. A bit about the project that I want to showcase this morning. It is a project that is in the late stages of delivery on the Gold Coast, southeast Queensland. This project's an interesting one for us in that it's quite complex. It's a brownfield site. It's existing. It's a tight corridor. It's fairly high profile. We've got state and local government representation. We've got a lot of different owners and operators that all have competing drivers. But what's not obvious on this project is that there's significant work under the ground that we don't really associate with a project like this. Existing infrastructure under the ground, drainage, public utilities and the like, which is all has its own drivers in coordination. This is sometimes what it feels like to try and coordinate this work under the ground. I just thought I'd throw that one in. You can see the complexity that we deal with. Some of the project metrics, just quickly. Some of the numbers, there's about 33 different stakeholder companies across 4 countries. Sorry if I read this. 14 cities, about 120 different design packages. Now those design partners are sharing about 400 different models across 9 different authoring applications in a civil space. Importantly, we made the decision at the start of this project to exchange in one format being IC. And I'll explain why that became relevant as we move through. Quickly on a DE-related side of things for our ecosystem. In the centre of the screen was the John Holland CDE, which this project was. I don't know how popular that is in this region, but all our design partners were feeding into this CDE through a 4-gate milestone process, all the native and all the exchange files. As we move down through the centre of the screen there is an element in the middle, an automation layer that I want to expand upon during the session. And that content then fed onto our 2 forward-facing platforms, our collaboration platform, this project with Visto, collaboration issue tracking, and then our GIS platform, the interoperably platform. So just talking more about that automation layer, that was broken down into a IFC patching piece, which you can see in the dark red, and also a automated IFC generation piece as well. On the patching side of things, we had to, some of this was by necessity, and some of this was, and most of this was just to add some value on our delivery side. So I'll talk through these quickly. One of the elements, one of the use cases was pushing calculated data into a consistent property set that we could retrieve in a consistent manner and trust the data. So we were calculating week to week content like positional data, change data, invert depths, assembly lengths, widths of elements, and this information has been pushed into a single location. So it wasn't relying on authoring application content, it was calculated data. At a container level, we're also week to week pushing our CDE attribution through to elements as well. So we can understand design progression, we can understand visually what stage elements we're at, what packages we're at. So really important when you're moving through your design progression to understand where packages are at in the progression and make informed decisions around that. This one here, I'll spend a little bit more time on. This was where it all began for me personally. We had an issue with changing builds. Now this was a result of our authoring packages in civil space, often creating geometry on the fly in a destructive process. So when it says destructive, they were at the time of export, they were generating content from strings, from 2D strings, and hence creating new builds. So you can imagine the issue with that. This was back in about 2022 when we first had this issue. So we were sort of forced to look at, well, how do we define uniqueness of elements outside of global IDs or builders or machine generated builders. So what we came up with was looking at the geo-located bounding boxes, or the access line bounding boxes in 3D space, coupled with a couple of other indicators of uniqueness. And that was then our go-to for, is an element the same one rather than build. Now, once we defined that process, we could then start looking at the GUIDs, because downstream applications were still using the GUIDs, so we could then patch previous GUIDs to, if they changed, to the current, swap out the GUIDs. So we were maintaining a registry of GUIDs basically for all elements across all files, across the whole design process. So that's basically solved the issue pretty much from day one for things like issue tracking, budget detection, any 45D workflows that were heavily reliant on element builds. Now, a knock-on effect for that for us was that now we were being able to track positional change, which was really nice because now at a file level down in an opening file, we could understand what percentage of elements are physically moved. We could do that at a package level, we could do that across all 400 files, and obviously dashboard that and get some real insights when we compare that to milestones, understand something that been approved for construction, things change from a positional perspective. We start asking questions as to why. So that was quite a powerful piece for us. From an automated IFC generation piece in the construction space, temporary works is really important, especially when you're in the ground. No point in automating temporary works if you don't understand what it takes to build it. This example is one with drainage and being able to programmatically repeatedly create content, in this case shoring boxes for drainage, and spatially sort of coordinated against that. Our survey function is hugely important, so this is a use case of pushing some visual indicators into the collaboration platforms for quality level. So quality level, I'm not sure what it's called in this region, but for us, it essentially gives you an indicator of how much you trust that content on the ground. So has it been surveyed, has it been physically potholed, bucketed up, and surveyed. So we were creating visual indicators that had attributes attached to them, items like hyperlinks to where the source data for pothole content could be found. So our user group could easily just use that, click on open up the source reports and save a lot of time. This one I'll include, I quite like this one. This is a really taking really unstructured data. This is a Word document for Argus reports, and pushing it through a repeatable cycle, it's a repeatable process of being able to generate content that includes things like is the tree being retained, is it being removed, what's the structural root wall, what's the structural protection zone. Really important stuff when you've got trees that aren't being removed and you cannot encroach certain ground areas from your services. Similar vein, exclusion zones overlooked. So if you can quickly create the geometry around all these types of exclusion zones, another hugely valuable piece. I haven't touched on the data side of things, but we used IFC and IFC OpenShell in particular Python to get a window to files and create some transparency around the completion of data. We had really significant data requirements both on our side and on the client operations sides. GIS was again really embedded in the IFC workflow. And just to wrap it up, from a survey perspective, all our case constructed data was being picked up. Not only was it being exchanged in IFC, but it was being attributed whether it was live or not. So we were feeding all this content back into our collaboration platforms that not only is it constructed, but is it live, is it pre-existing and being retained, is it new works? So quite a valuable proposition as well, valuable data set at the end of the day. So I'll leave it at that. Thanks very much for your time.
Thank you, Nathan. And the last finalist in this category is China Academy of Railway Sciences.
Good morning, everyone. Let me introduce myself. My name is Liu Wei, and I am currently working at the China Academy of Railway Sciences. Today, I'm going to present my project, application of multi-dimensional management for super large railway project clusters based on openBIM. My presentation consists of 4 parts. First, Ping project information. Guangdong province is the most economically developed province in China. By the end of 2024, the total length of railway project has reached 5,964 kilometers, with a total investment of $146 billion. Currently, Guangdong is making every effort to advance the construction of 10 King Railway projects. When the owner manages high-speed railway constructions, there are issues like low conversion efficiency and cross-stage data loss. Thus, 5 system development for assets, including reusable management method and support for matter-level multi-unit conversion. To solve this issue and meet goals, openBIM-based plan in the proposal and a data sharing and comparative management system is successfully built. There are leaders of our core team. Key information about the openBIM. According with the ISO 19650, the project identified the information requirement and successfully achieved ordinary iteration from design to operation and maintenance progress from OIR to AIM. To achieve data interconnection and issue collaboration among all parties, we have built the CDE with information at all stages achieved in the Guangdong Provincial Railway Engineering Management Platform. We have developed the RACI responsibility matrix to clearly define each entity responsibilities in information management activities. As shown in the software ecosystem map, in the early stage, the IDS is used to standardize information delivery requirements, and the PSDD is relied on to build and install the railway field terminology system. In accordance with China Railways technology standard, we have extended the objects, classifications, attributes of PSDD for the railway sector, thereby establishing a standardized set of terms and the definition applicable to all railway projects in Guangdong. We first identify professional categories by construction process, then expand the definitions attributes of these categories. The PSDD serves as the basis for FC modeling requirements and IDS detection. We studied how to map FC standard to complex railway BIM models, enrich and extend the semantics of FC models, and ensure they meet the unique requirement of railway engineering. Application of FC have solved problems. When different participants use a different software for modeling. To date, we have completed 520 million FC components and standardized the attribute of various types of FC components. Based on the data need of various participants, we developed a delivery manual that covers not only traditional physical requirements, but also AI-oriented specifications for accurate retrieval. To ensure the quality of model submits by all participants, we have developed IDS verification tools that automatically verifies whether FC model compared with specification and generate report. We developed a PCF-based issue management platform that streamlines issues, circulation, and supports collaborative resolution. In addition, we integrated AI technology to assist the frontline personnel. The system generates reference solutions for design team and provide AI-powered intelligent Q&A across the issuer database. Key outcomes. Our project have achieved 4 outcomes. First, we established an automatic association between FC models and engineering entity decomposition using PSDD. We standardize FC model attribute and attract key attributes to link them with the engineering entities decomposition. Second, we achieved efficient collaboration across all business areas, taking design change issues as an example. Processes such as initiation, evaluation, modification, and the result review will all be carried out seamlessly on the PCF platform. Third, schedule early warning with openBIM. We use the openBIM system to standardize data and presence. Then with the knowledge graphic and the cluster analysis, we extracted the schedule-related issue from database and identified rules. This is a knowledge graph formed by various factors, affecting project schedule and engineering structures, engineering entities. Fourth, realize the integration of openBIM and AI. OpenBIM ensures high quality and standardized data. serving as a reliable knowledge source for large AI model. After training and interference, the models can predict calibration issues, generate construction plans, and recognize schedules. This greatly enhances the intelligence of railway engineering management. This is an example of integration of openBIM and AI. The video showed AI automatically generating construction precautions and alerting on safety risks based on model information, on site matches, and the construction safety specification. We enable AI to build the properties of specific components based on standardized FC models, and also allow AI to directly code up the models for viewing. With OpenCD API, BIM data becomes standardized, shareable, and accessible. AI leverage natural language understanding to translate users' instructions into intelligent BIM operation. For example, like highlighting pair caps, locating pair number 8, retrieving its attribute, and generating construction guidelines based on these attributes. The combination of AI and OpenCD API not only makes data reasonable, but also truly intelligent, advancing railway engineering towards a new era of smart collaboration. Finally, let me summarize the application of value of this project. Benefiting from the application of openBIM, we have successfully improved the delivery efficiency and the quality of operations work such as design and constructions. Ultimately, we have reduced the railway construction cost with the average cost have successfully established a standardized mechanism based on openBIM that supports cross-project replication, multi-party collaboration. More importantly, the integration of AI and openBIM has made BIM data truly accessible effectively, improving the efficiency and the frontline workers. This is not only a breakthrough for the project, but also a crucial step for the industry towards great efficiency, transparency, and collaboration. Thank you very much.
Thank you. And if Nathan would like to come again and some more Q&A from the jurors, go ahead.
Thank you for the presentation. Very good. Thank you. I wanted to start with the Holland project. I myself am from the Netherlands, so I understand what you're getting in the underground, and I also had a question about that. What was the existing tolerance of the underground structures/cables? And did this lead to any major unforeseen issues? And how was that fed back into models and back to the data partners?
Thanks for the question. So depending on the asset category, they have their own tolerance requirements. So there's a complex matrix of horizontal and vertical tolerances are. So we use to manage that side of things. There's flash detection piece that we run through. We also have an issue tracking platform dispensation because being a brownfield site, something's got to give. So not everybody, you cannot provide with everyone. So you need to seek dispensation from different property owners. So we were using issue tracking, and that was one of the elements that started to fall apart. We were changing the traffic and we have issues close when we have the same one. So the policy. That's a little bit. Okay. Thank you for the presentation. I have a question directly for second one. You have mentioned or you showed that area is where the geometry for reservations, like the security zones, and no-go zones, let's say. I hope you are familiar with the IFC spatial zone, and there is a technical report of that, BSI technical report. Have you matched that stuff with that report, and especially with that entity or the class? Have you used that one, or you matched your own classes and In short, we were just generating fairly young geometry for that side of things. So it was really just for us, for our guys on site to be able to it's something that we need to. So this was additional to our design deliverables. So in an ideal world, you would have that spatial classification built into the on-set boxes that need to deliver to you. We weren't getting that. We made a decision just from a time perspective that it wasn't worth the effort to go back and trip that. We would just feel like getting it in there because very tight delivery schedule for us. And we were also pushing a lot of other things that really weren't on our radar when we first started the project, and having access to the IFC and open the process really gave us a lot of value that we could start generating stuff ourselves.
That would be a recommendation to check that IFC spatial zone, especially construction and security.
Question for you. Maybe for this, you showed a lot of use cases of AI and large language models. I was wondering how you would want to control the accuracy of the outcome of these models. How do you check that? Curious about it.
这个准确性的问题，主要其实通过这个 BSDD 去控制它的这个准确性，然后在这个 MVD 就是它的子集上，我们去把这个所有的属性呢都聚焦到这个模型构建上，这样的话它就不会有幻觉，可以从50%-60%的这个准确性提高到90%以上。
I will translate his answer. First, we will use the BSDD to improve the accuracy of the large language model, and we will mapping the entity points in the MVD, and then we can improve the efficiency, and we can eliminate the illusion of the LLM. They can to ensure that the accuracy would be increased from 50% to maybe 90%.
Okay, you mentioned BSD, that's why I would directly ask the question to BSD. It's a great job you did there, and have you expanded it for later stages, like for operation, using BSD for to operate the railway as well, or is it just for construction phase?
You mean the BSD to extend DD to
use it on operation phase?
这个是考虑过的，尤其是在交付这个就是我们现在叫电子档案这个数字资产，数字资产之后呢，这个数字资产的价值发掘呢，主要通过 AI 和 BSDD 它们相互的这个关系呢，可以发挥这个数字资产全生命周期的一个价值。在这个项目上，我们也拓展了一些这个就是竣工交付数字资产的相关的一些 BSDD。
First, the answer is yes, and based on the BSDD plus the AI, and we explored how to how to collect the requirements from the operation phase, and then we can combine it to our construction phase, so that we can make we can add the data and the information that will be considered by operation phase into our construction model. So yes, we explore some we can see the property and some attributes which belong to the operations and make them in our BSD.
One final question.
Okay, thank you. One of the most complex things within real buildings is when the rail goes into the building. How did you combine that with the multidisciplinary part, but also with the real domain and what things were missing in the real domain?
I would like to confirm your question. So it's about combine or federate the model between the building and the rail.
在这上呢，我们自己研发了一个装配的软件，这个 Reworks。通过 Reworks 呢，这个它去这个检查，就是装配来自不同这个建模软件的模型，并且在这个 Reworks 呢放了检查的工具，就通过检查工具呢来检查是否符合这个 FC 的相关的标准，属性有没有缺失。因为这个装配软件是我们自己研发的，所以它的可控性也比较好一点。
Okay, so we developed software called Reworks. We can combine, we can federate the different model in this software, and because it's developed by ourselves, so we can better control the different model in the same workspace.
Thank you very much.
Okay, thank you to the two presenters in the category of construction for infrastructure, and that does conclude this session. So we will now wrap this up. Jury are going to go away and deliberate, and we will be back in around 25 minutes for the next categories. Thank you.